So now we're going to classify functions. All right? So I certainly am supposed to teach this in 3101, and you're supposed to know it when you get to 3101. So I don't know how many people know big O notation? All right? Good. So this should be easy. We're now going to define big O notation again in 2 slides. All right? Maybe 4 slides. Anyway, this is what we wanted to find. Right? What do we want to see? Here it all is. And when you learned it, did you learn some ugly thing like this, or did you wave your hands around? Did anybody see this? Did anybody understand it? All right? Well, now, hopefully you can understand it. All right? So let's understand what this means. Right? So we want to say, what do we want to say? We want to say F is more or less G within a multiplicative constant. Right? So what we want to say is F is sandwiched between G times some big constant. So here C2 is like a billion. And its G is always bigger than a little constant times G. Right? So everybody got this part here? Right? We want F to be sandwiched between them. And you can see here, more or less, except for the beginning part, F is between these two sandwiched. Right? So that's what we're saying here. F is sandwiched between those two. Now you want to say, well, which constants? Right? I've given the example here. Well, C1 you can think is going to be really little, and C2 we're going to think is really big. But how big can they be? Right? Is there a limit on how big they can be? No, they can be any constants. So all I'm saying is that there exist constants. Right? I'm kind of lying a little bit because I'm implying that they have to be bigger than 0. All right? So this guy here, if you made it 0, it makes the whole thing kind of boring. Right? So these constants have to be bigger than 0. Right? Now, you might think that seems unfair because if they can be any bit size, then surely we can sandwich this function. Right? Because you just make the C's bigger and bigger. Right? But the trick is the game. Right? The trick is you have to fix these constants. You have to fix them once and for all. And then it has to work for every n. All right? So here, we're saying that's great. But once you fix the constant, it has to work for every n that's sufficiently large. All right? Now, everybody got that part? Right now, what's the sufficiently large part? Well, the feeling is that when n small, things might just be bouncing around and we haven't really gotten a pattern yet. Right? So we only need n to be bigger, it to be true for every n bigger than some n naught. Often we use n naught for the beginning n. Right? And which beginning n are we talking about? I don't care. You can choose any beginning n you want, but you have to choose it at the beginning. Right? So does that make sense? Right? The game is you have to choose the constants in the beginning, and then for every n bigger, it has to be true. It has to be sandwiched. So just to do a concrete example here, right? We all know that 8n squared plus 1000n is big O of n squared. Right? You know that. Why? Because the 1000n is low order and you drop it. And then the 8 is a multiplicative constant, so you drop it. Right? And how do we prove this? We prove it by we have to come up with these values. Right? So, and there's a toss-up here. Sometimes you can make the C bigger and the n not smaller, or you can play it. I like to make my c as small as possible, right? And why did I make it 9? Well, 8 just won't do the trick, right? And I could have made it 8.001, but I rounded up to the next integer, right? So I made C9. And now, then I have to fudge what this has to be, right? And you can see it's because we have to deal with that, right? So now we can make n bigger than any number bigger than 1,000, right? You see how we're playing the game, right? And now then we have to prove that we got our thing. And this whole thing is less than or equal to this. Why? Because n's bigger than 1,000, right? And then this sums up to this, which is what we need. Right? Everybody see that? Right? And see, we needed a fixed c that worked for all n. All right, so here's another statement. Just, is this true? Right? Is 2 to the n bigger than big O of n? No. No, everybody should know that's not true. Right? It's not true. You know I write things that aren't true. Right? So if I were to try to prove it, right, I can make my c really big. I think, hey, no problem, I'll just make my c big. And then the adversary can say, hey, look it, you can make your c as big as you want to make it, but I can make my n bigger. Right? So he can set n to be c, and then we'll see, well, we all know for reasonably big n, 2 to the n is bigger than n squared. So it's not true. Right? Everybody buy that? Now here's another one. Is this true? The last line. Is it true? We got some yeses and some nos, right? Now let's play the game. He's wanting to make it hard, so he's going to make n be some really big number, right? Really, it's some arbitrary number. Let's think about this as some arbitrary number. That's what he's supposed to do. And then, now for a fixed c, for a fixed n, I can make c really, really big here, right? So now I can make c be 2 to the n, and we have that the statement's true, right? Because the difference is you can't have a different c for each n. Right? Everybody good with this? Yeah. Oh, so let me say what I just said in 3101. You know, out in the quiet, I don't know if it was for this course, but certainly for 3101, a couple people whispered and said, you know, I only understand a third of what you say. Right? So what do we do about that? You know, you guys could study more, you could think harder, right? But really what you need to do is you need to ask me more questions. All right? So this course, just like I said in 3101, we're starting off easy, right? We're going to get much harder, much, much harder. All right? So what you need to make sure you do is minimally, as the slide goes by, you should understand it. All right? So it's everybody's job in this room not to let a slide go by that you don't understand. All right? Can we commit to that? Everybody who commits to that, put up your hand. See? Good. You all know how to put up your hand. All right? So don't be shy. Is everybody understanding what we're doing here? Okay, let me show you. So this is just saying theta means you're bound on both sides. Omega means you're bound on the top. Oh, no, big O is bounded on the top. Omega is you're bounded on the bottom. Little o means you're really, really smaller. Little omega means you're really, really bigger. So here, let me just tell you some notation that I like to use and that you probably haven't learned. All right? So theta of 1, everybody remember what theta of 1 means? It means it's bounded by some constant. Right? So the theta of 1 is bigger than 0.001 and it's smaller than 10. Right? Smaller than 1,000. So what do I mean by this? This means the class of all functions that are here. Let's write it down, what it means. I'm going to say it's polynomial time. It's n to some constant. Right? What's a polynomial? N to some constant. So what's the formal definition here? There exist two constants so that for all big N, f of n is bigger than n to the one constant and less than n to the other constant. Right? Does that make sense? Everybody following that? You know, it's just nice notation. And here's another thing. We could talk about 2. So theta of n, you know, is some constant times n. Right? So 2 to the theta of n is 2 to some constant times n. And I'm claiming 3 to the n times n is part of that. Right? You might say, oh, well, this is 3, not 2. Right? But if you do some ugly math things, you can bring that this is equal to this. You kind of bring the 3 up. And now this thing is has an n in it, so is order n. Anyway, it's just this is nice notation to mean exponential time, right? And it means we got some constants so that f is sandwiched between 2 to the constant times n and 2 to the constant times n. It's sandwiched between them. Everybody got that? Yeah. All right, so now we're going to talk about computation because that's what this whole course is about. All right? So what is a computational problem? You definitely need to know because that's what we're doing here. We're solving computational problems. Computational problem is, I did turn on the mic, didn't I? Let's get that. Did I do this? I did? All right, we're good. All right. So what's a computational problem? For every input, I tell you what the output is. Right? That's a computational problem. And generally for this course, we're going to assume that inputs are binary strings and outputs are often yes, no. But, you know, we could have the input be elephants and the output be the color of the elephants, right? I mean, you could have any function here. Oh, I didn't finish this page. All right, so what's an algorithm?